So members will have this particular problem saying the simply supported beam in figure A carries two concentrated loads, then derive the expressions for the shear force and the bending moment for each segment of the beam. Then sketch the shear force and bending moment diagrams. Then we are being told to neglect the weight of the beam. In a real sense, what we deal with in the practical world, the weight of the beam is always big. So we cannot neglect it, especially when we are dealing with the real or practical problems in the real world. But here, for purposes of academics, we are going to neglect the weight of the beam. So let's move. Now we have a beam that is showing us points A, B, C, D. We are given that at support A, there is a support which is a hinge or pin joint. Then at the end, at point D, we have a roller support. So this one is a hinge joint. Then this one is a roller support. Now, at B, there is a load, a concentrated load of 14 kilonewton, then 28 kilonewtons at C. Now, we are required to, first of all, draw a free body diagram for this. Then after drawing the free body diagram, you indicate the forces and go ahead and calculate the unknowns. The unknowns are always the reactions at the support. And now if this one is a hinge joint, then it means you have a reaction in the x direction. You also have a reaction in the vertical direction. Whereas at the roller support, you always have only and only a vertical reaction. Now let's go ahead and maybe draw a free body diagram for this. Let me go to shape. Okay, so I've said we have a vertical reaction which we are calling maybe a y, and we have a horizontal reaction which we are calling ax, because we have a hinge joint here. Then we are also going to say, since this is a roller support, we shall have a reaction that we are going to call dy in the vertical direction. Then again, we are provided with the concentrated rods. This is A, we have B, we have C somewhere, and this is D. At B we have 14 kilonewtons. Then at C we have 28 kilonewtons. And you have to indicate these distances. We have 2 meters from there to there. Then you have 3 meters from there to there. Then you have 2 meters from there to there. So members, you have to remember the conditions of static equilibrium, because this beam is statically determined. So recall static equilibrium conditions, whereby the sum of forces in the x direction must equal to 0. The sum of forces in the vertical direction must equal to 0, and the sum of moments about a particular point must also equal to 0. So having known or remembered these static equilibrium conditions, then we need to go further and state the equations, the underlying equations that are going to result into calculation of ax, ay, and dy, because we cannot go ahead and calculate for shear forces and bending moments if we don't know what is the value of the reaction at D and what is the value of the reactions at A. So we proceed and say we start with the one in the x direction. So if we consider sum of forces in the x direction equal to 0, then we only see that the only force acting in the x direction at support A is AX. The other side we don't have any other. So it means AX is equal to 0 for equilibrium conditions. So we shall go ahead and say 1, we have sum of forces in the x direction equal to 0. Then we have AX, which is equal to 0. That is 1. We move. We say summation of forces in the y direction, sum of forces in the vertical direction should be equal to 0. It is the same way of saying that vertical upward forces are equal to downward. So I just go up here and see which ones are downward forces and which one are upward forces. AY and DY are upward forces, whereas 14 and 28 are downward forces. So I will come down here and state my equation as AY plus DY is equal to 14 plus 28. And this is going to be 42. So this is going to be AY plus DY is equal to 42, and I call this equation 2. Then I also go to the third condition and say sum of forces, sum of moments about a point must equal to 0. The 14 and the 28 kilonewtons forces are in a clockwise direction, whereas the dy is a reaction that is acting in an anti-clockwise direction. That is, if we take moments about A. Why do we take moments about A? We already have so many reactions passing through A. And you remember that if we are to get moments of a force and we take wherever we take moments and there is a line of action of a particular force, then the moment of that particular force where its line of action is passing and it's where we are taking moments, it shall not hold, because there is no perpendicular distance that that force is going to move from that particular point. So its moment about that point is going to be 0. But the other forces that are far away from that point and their lines of action are perpendicular, to the axis passing through that point, then for them they are going to have their own moments, and we are going to calculate them. Now, what does that mean? It means dy has a clockwise moment, whereas 14 it has an anti-clockwise moment, whereas the 4. Let's go down and write that equation, which is the third one. So we are saying we have clockwise moments must equal to anti-clockwise moments. Now we said we have the clockwise moments being the 14, now times its perpendicular distance from where we are taking the moments. We have our moments being taken at A, so if we are saying we have a 14 in a clockwise direction, its moment will be 14 times 2. Likewise, this 28 will also be in a clockwise direction, and it will be 28 times the distance from the point where we are taking moments, and that is 2 plus 3 to become 5. So let's go down. Let's admit some members into this discussion. Then we proceed and we write down that equation. So this is, we have said this is 14 times 2, then plus 28 times 5. Okay, which is equal to dy times the perpendicular distance from A, and which is that distance, let us see. It is 2 plus 3 plus 2, which becomes 5 plus 2, and it becomes 7. So it will be 7 times dy, or dy times 7. So now, from here, this is going to be 28. This is going to be, let me use my calculator. 28 times 5. This is 140 equal to 7 dy. Meaning that my dy is going to be 168 divided by 7, which gives me 24 kilonewtons. Okay, then I can use now the other equation number 2. I can say from 2, my ay is going to be what? It is going to be 42 minus dy, which becomes 42 minus dy, which we have just calculated as 4. Okay, 4. And what will that be? This is going to be 18. Yes, it is going to be. So you have, at the end of the day, calculated the reactions at the supports. Now your task is to maybe redraw the beam, and now indicate all those forces, and this is what we are calling a free body diagram. So this one is going to be a y. Ax is 0, so even if we don't indicate it right now, so our ay is 18 kilonewtons. Our dy, we have seen that it is 24 kilonewtons. Then we have this being A, this is D, we have C somewhere, which is 14 kilonewtons, and it is at 2 meters from A. Then from C we have, okay, this, okay, B. Then we have C somewhere, 20 newtons, and we have 3 meters. Then we have also 2 meters from C to D. Okay, this is my free body diagram. That diagram that shows the representation of forces on the diagram or on the structure itself. So our task is now to calculate what we are calling the bending moment and shear force, shear forces or shear force loads on the structural member. Now we are going to use method of segments or sections. What does that mean? I'm going to divide this beam into several sections. Okay, from A to B, that can be a segment. B to C, that can be a segment, and C to D can be a segment. But in the middle there, we are going to have sections. Okay, and I'm going to call, for example, maybe this one, call it X, so that I'm just analyzing. I want to analyze what is the shear force between, as you go from A to B. What is the shear force and what is the bending moment around there? Even if I move the cross to this, it will still be the same because it is still between A and B. Now, for me, what I will do, I will go down there. Maybe I can call, if this is segment 1, I can call it maybe this x1 to say that this is my section 1. My section 1, then I can now come and maybe draw it down here. Let me draw it. Where are my shapes? Let me draw it here. Okay. After drawing it, I can pick my pen. Remember, I have a force here, a force which is already calculated, and that is AY, which is 18 kilonewtons. 18 kilonewtons. Okay, then this is A. I say this was my section. My section was, okay, this was my section x1. But if I indicate it as that section, then I need to also indicate that it is at a distance maybe x from A. I'm trying to analyze. I want to know what could be the bending moment at a distance x. Okay, in x I can say, since this is 2 meters, I want to analyze what is the bending moment at 1 meter, at 1.5 meters, at 2 meters. That's why we introduce in x, so that will develop maybe an equation that will lead us into formation of a bending moment, or calculation of a bending moment in between there, because it is so much important to us. Then if we cut, because if we do the sectioning, it means we have cut the beam at that moment, or at that point. So what happens? Okay. Let me refresh my computer here, because my pen is okay. Let's proceed. So we have said if we create a section, then it means we have cut a beam at that particular point. So if we cut the beam at that particular point, we have said let it be a distance x, let that section be a distance x. We are looking at AB. Okay. Our members, let's move. Okay, let's look at from A to B, the segment AB. If we cut in the middle of segment AB, then that section that we have created is going to be at a distance x from A. Then maybe what I can say, this is segment B, or what we can say is distance 0 less or equal to x less or equal to 2. Okay, it is less or equal to x less 2. We are looking at a section, or that segment, which is at a distance of less than 2. In other words, we are ranging between 0 and 2. Okay, now if we do that, we said we have a shear force here, and we have a bending moment that way. My shear force, okay, let me maybe make it move down. Usually what we do, we make it face it down, okay? Then you make this one a bending moment. Remember, this one is a V, or what we call a shear. Then is back. So we say that we have a segment AB of 0 less or equal to x less 2. We have said our shear force is going to face down. We are assuming what if it is facing down, then why is the bending moment going like that? Of course, we are trying to find a way of counteracting the effect of this shear force. Likewise, on the other side of the beam, we can always show it. But now what happens is that our shear force is now facing the opposite direction. Also, the bending moment is going to face the opposite direction. So that at the end of the day, in the beginning I told you, if this is a plus and this is a minus, the two will cancel each other and the beam is in equilibrium as far as bending moments are concerned at that point. Likewise, with the shear forces, if this is maybe negative and the other one is positive, they will cancel each other, and at the end of the day, we shall say everything is in equilibrium. Okay? So let's move. Now I'm saying if this is a bending moment and that is a shear force facing down, you need it now to apply equilibrium conditions. Sum of forces in the y direction should equal to 0. Meaning that if I have my 18 facing upward minus v, this is going to be equal to 0. Members, let us admit someone who is requesting enter. He has come in. So v is going to equal to 18 kilonewtons. So for the segment AB, in the space between 0 to 2 meters, the shear force is going to be 18 kilonewtons. No compromise. It's going to be a constant up to that particular point. Then how about the sum of moments should also equal to 0, meaning that I will have 18, which is going to have, okay, maybe, let me repeat this. For moments, I'll just hold here at this point A, so that at the end of the day, I have the shear force taking place in the equation, and then the other BM. How does that one work? If I take moments about A, and I take clockwise moments to be positive, then this is going to be Vx. Okay, the line of action of V is at a distance x from the turning point. So it will be Vx. Then this bending moment is in an anti-clockwise direction. Minus m is equal to, that's why I will say that my m is equal to Vx, whereby V is 18. So my m is equal to 18x. If I call this one as maybe equation I call this equation 2. I proceed to another segment. So if I consider, for example, segment CD, okay, maybe B. I have maybe jumped BC. So let me say that is at a distance 2 less or equal to x less 5, because up here you can see that the distance lies from, for example, 0 at A to C. So C, it will be 2 plus 3 become 5. That's why I'm saying I'm looking at the distance from 2 to x to 5. So the distance of 5 stops here, and that is segment BC. That means I will be create another section around that point. Maybe I call it section 2. X2, which if I draw the free body diagram, this is how it will look like. I will have beam like this. I have A with 18, then I have another force at this is A, then I have at B. At B, I have a 14. Then this is B. So I create a set here, which I have X. Because I'm analyzing between B and C, that's why I don't complete up to C. I need to know what is happening between B and C. So here also, I will have a shear force and a bending moment. M. Let me pick another pen. Now, what happens here? I have a 14, and now from A to this section, you can call it X, distance X, such that I have to look for forces, the upward or downward direction, or vertical forces. So if I look at forces in the vertical direction, then I will have, for example, 18 upward forces are equal to downward forces, equal to 14 plus V, such that my V is equal to 18 minus 14, and this is going to be what? This is going to be 4 kilonewtons. Maybe I call equation 3, then I go to what is now the bending. Now the bending moment, I'm going to take moments about A. This is A. The other one is B and C. So taking moments about A, I know I have to hold at the end here so that I have V taking part in the equation. So I'll hold here and say clockwise moments I have Vx, then plus 14, the distance from here there is 2 meters. So I need to indicate it also there so that I have now plus 14 times 2. Okay, those are in clockwise direction, then minus m, which will equal to 0. So at the end of the day, I want to get the equation for the bending moment. But remember, V have already calculated for it, so I'll just substitute in here so that at the end of the day, I have m, which is going to equal to my m plus 2. My m is going to be 4x plus, call this 4. I can proceed to segment D so that I have that segment that may be between 5 less or equal to x less 7. Okay, then I draw it also. So here, remember, I have 18 Newton. This A, I have B, I have C. Then D is continuous. So at B, I have a force for the distance of that from the end A or from support A. Then I have a force 28 kilonewtons at a distance of 3 meters from B. Now, if I went here, I would also indicate a section, maybe x3. Maybe I come here and say between C and D, a section maybe K. Here, so this is a section. If this section, I have a shear force there, and I have a bending moment M. What does that mean? In writing down now my equations, I need to consider equilibrium conditions. I say for upward forces, then I sum, okay, for vertical forces, I sum upward forces, I say they are equal to downward. So meaning that 18 is going to equal to, this 18 is going to equal to V plus 14, so that my V equal to 18 minus 40, and my V is going to equal to negative maybe kilograms. So if V is equal to negative 4 kilograms, maybe I can call this equation 5. Then I talk about moments, about such that I develop an equation for bending moment on this segment that we are saying is CD. So what will happen there? It will be, now when we take clockwise moments, holding here, I will have clockwise moments being 14 times 2 plus 28 times 5 plus V times X. Okay, because from here to the line of action of the shear force V, we are calling it distance X at this segment, which we called X3. Okay, so what is this one equaling to? Equal to the bending moment M. So just work out this. This is going to be Vx. Okay, this is 28 plus 140, that becomes 168. Then minus 24x, because V is minus 24. So my M is going to be minus 24x plus 168. And I call this maybe equation 6. I think I'm through with that. But even if someone never wanted to write all this, you can go to maybe the end and draw this segment CD, which you draw the other end. Okay, remember here we said this 4, and if we indicated that the other side, maybe then tap here so that remember alongside the other segment or the other section. Okay, let me redraw it apart as well. If I drew it this is 15. This is we said 14. Then we said this is 28, and this is A, this is B, this is C. Then it means we are still lacking some last portion. There is that last portion that has D. So this is 24. According to what we calculated, the reaction there is 24. This is 2 meters, this is 3 meters, from there to there, from there to there is 2 meters. Now we have a section in between here that we called x3, x3, or just a cut. So if we said this is V and M is in that direction, then likewise this side, our V is going to point upwards, like we said, and therefore also M will point in that direction, because what we have showed here, when I said when we add the two moments, they should be equaling to 0, or they should cancel each other, because it is the same moment, but because we have said we are considering one side of the section and another side of the section, the two, if we consider sign conversion, the two are going to be equal in magnitude but different in sign. So they will cancel each other and still will maintain the state of equilibrium. Likewise for V, if this is positive and the other one is minus, they will also cancel each other and we still maintain a state of equilibrium at that moment, or I mean at that point. So now what happens to this particular point if we said this is X? If this is X, and the whole beam from here to D is 7, then it means this distance is going to be 7 minus X. So if we want to, one can use this other side, another one can use the other side. As long as you have used the sign convention properly or interpreted it properly, then you still have to get the same equation. So let us use now this portion that we have created and see if we get this particular equation. Now what happens is that we need to also look for upward forces and downward forces. The upward forces being positive, we shall say V, then the other one is also upward, so we add there 24 equaling to 0, meaning that our V is equal to negative 24 kilonewtons, as we have already seen upwards there. What about moments? For moments, we are going to take moments about this point D, moments about D, then taking clockwise moments to be positive. Then it means my bending moment, which is facing in a clockwise direction. See, this is a clockwise direction. So what will that be? It will be M. Then that M, we add there V times 7 minus X. And this should equal to 0. So my M should equal to minus V into 7 minus X. If I know the value of V as negative 24, then I substitute it in here and complete that equation. So let us substitute in the value for V. It is negative 24, so my M is equal to negative times, negative 24. It becomes negative 24 into 7 minus X. What is this? This means M is equal to, remember this now becomes a positive, so times 24 times 7, you get 168. Then 24 times minus X, you have minus 24X. So what does that mean? it means that my M should equal to minus 24x minus, okay, plus 1, as it had already been calculated from up here. So whether you use this side or you use the other side, you'll get the same bending moment. Because I said the bending moment at that particular portion is the same, whether I take the left of the section or I take the right of the mat to give. From where we started up to this point, is there any question, dear members? Gotten. Maybe to just wrap, if this still was not clear, I said if you draw your free body diagram of the segment, you need to include also the earlier parts, the other portion. If we are considering CD, you see I've drawn the part for A, B, B, C, because those ones I already know the forces acting on them and I've already calculated the shear force. So I'm now on portion CD, so I just look at the beam from the left. So I go to between C and chop, or I cut the beam. So if I cut it at that point, then I will have C and D now separate, okay? Meaning that I can draw the portion of the beam from A to C, to C, then I extend some portion. Remember, if this is C, then there is some portion continuing, showing us that we are analyzing between C and D. Then the other part is moving from where we cut D. So if I indicate my internal forces or internal loads, the bending moment and the shear force, the shear forces within that beam or that section, I indicate the proper sign convention on this other side, on the left side. Then if I also choose to draw the other portion that is remaining, I also need to show the correct or follow the correct sign convention. I'm saying if I consider the bending moment moving the other way around and the shear force moving downwards, then the other side, the bending moment will move the other side opposite to this, then also the shear force will move upwards. Then if I said that section is at a distance x from A, then if the other last part reaches up to D, and I know if I add this part and that part makes a complete beam from A to D and its length is 7, then if from A to that point is x, then it means the remaining portion will be 7 minus x. So if I indicate the right conversions, then I carry out I apply the principle of moments and other equilibrium conditions, then I should get the same equation for bending moment here and shear force like I got from this particular portion from A to where. So ladies and gentlemen, if that one is very clear, let's go ahead and draw our bending moments. Bending moment diagram and the shear force diagram. Let me paste. Okay, so in doing this, usually you need to redraw. Okay, you need to redraw the free hands. So I'm going to redraw the free body diagram of the beam and indicate the forces that are acting A, and I have kilonewtons here, I have D, and I have about 24 kilonewtons, I have point B, and I have 14 kilonewtons, I have point C somewhere, and it is at meters there, this meters, then this is also meters to the end, and this is 28 kilonewtons. What I do when I reach here, can just project these points, just merge line dot, so that they guide when I'm drawing my bending moment and shear force diagrams. Okay, let's begin with the shear force. Let me write, remember that is a horizontal line. Don't say that line is hangouts. No, straight line, only that I'm using the free hand. So if I'm drawing the shear force diagram, I come here to the free body diagram. Now, The shear forces, we said they are just forces, and for this point, even at the point load, I mean at the support, okay, at the support there is a load due to the support, or what we are calling a reaction on the beam. Then there is a load that is external applied to the axis of the beam. Then we have reaction. What happens is that I have to move, I start from 0 and move 18 kilonewtons. So if I move 18 kilonewtons, I am going to first check. You will see that the bending, I mean the shear force at that position is supposed to be 18. Where is it? You can even check it here. Even without looking at the support, you can say from 0, okay? From support A, the shear force is 18. Then you draw it, okay? After drawing it, you need it also move up to point maybe B. Okay, if you reach point B, you see now what is the shear force there? The shear force is 4. So what happens, we are going to see how you can indicate that. Let's go down here and check our free body diagram. So it is here. We have said the shear force at A is 18. So you move. That's why we said it is between 0 less x less 2. So you move up to this point. When you reach this point, you find that there is a force which is called 14 kilonewtons and is moving downwards. So I'm going, remember I have come with 18, which is constant. Okay, I will draw a horizontal line to show you that it is constant up to B. When I reach B, I meet a force of 14 kilonewtons. So I am going to move by 14 kilonewtons downwards. If I move up to 14 kilonewtons, maybe this is 4. Okay, if I move 14 kilonewtons downwards, then it means if I get 18 minus 14, I'll remain with 4. So what is going to be here is going to be 4. Then I move again a horizontal line using a horizontal line, which is 4. Okay, this is 4, and I'm going to move from that point B to C. When I reach C, you know why it is 4? Because when we go to that segment BC, when you go to segment BC, you find that the shear force is 4. You can see from B to C, you see the shear force is 4. So even without you coming to check here, you can use those forces on the externally on the beam and tell that actually the shear force at that point is 4. Okay, or if you don't want to do it like that, you still come and say let me move 18. Then I say at the starting from B to C, even without maybe using, if you don't want to use my method of looking at those forces, you can just come after drawing your horizontal line, you have stored it there. Then you say between B and C, the shear force is 4. So you go to the 0 line, remember this is 0, and move to 4. So you move to 4 and move constantly. But at the end of the day, you will need to join this point and that point. Still, you will come up with the correct diagram. Then we move. After here, this is still 4. We meet a reaction. We meet an external load of 28. So 28 is moving downwards. So it means we are going to move from 4. Okay, we move 4 vertical up to 0. Then we add another value that will complete the 28. The other value that will complete the 28, when we add it to 4, it is going to be 24. So it means I will move I will move up to negative. That's what it means. So if I move up to negative 24, automatically when I check in between C and D, between C and D, you can see between C and D, the shear force is negative 24 and is constant up to point D. Okay, so me, I'm going to continue moving with my negative 24 up to when I reach point, I move up. But again, when I reach point D, I find there is a force which is moving up to D, which is 24. One thing you have to note is that if you find that you're drawing, okay, for these simple beams, if you find what you've been given, you're drawing the shear force diagram and it is not completing at 0. Or maybe you have a negative 24 and what you have here going upwards and stopping here, and this is the end of the beam. When you go upwards, you don't finish with maybe 24, then you know there is a problem. Let us take an example. You have got a negative 24 here, and this other part, it is given, for example, 30. Just know there is something wrong. So it means a shear force diagram will always start from 0 and always end at 0. Likewise, the bending moment diagram will also start from 0 and end at 0, except in maybe some cases where, for example, maybe the span given is not enough, or maybe there is a miscalculation in that particular problem. So let us now go ahead and draw the bending. So I'm going to draw here. If I draw a horizontal line, it means the bending moment is going to start from 0. Another point that you have to remember is that bending moments are always 0 at support. In other words, there is no bending at the support. Okay? There is no bending at the support. The bending moment can just be between the supports, or if there is at that support there is a rod and there is on one side and there is a rod on the other side. That's when you can talk about bending moment about the supports. But in these simple beams, you have got to always take the bending moment at the end is 0. But still, even if you don't want to maybe put that one in your mind, you still use these equations that you generated. So let us start from segment AB. Segment AB, the equation that is now going to allow us or assist us in drawing the bending moment diagram between A and B is going to be M equal to 18x. So you come and consider 18x here. 18x means that you're going to move a distance x from 0. So this is 0, this is 2. At 2, we have already said when x is equal to 0, if I put it in 18 times 0, the bending moment will be 0, right? What I earlier on. But if it is 2, I put 2 times 18, I will have my bending moment, maybe which is 30. Bending moment is going to be 36, and it is linearly increasing following the equation of a straight line. Actually, that bending moment m equal to 18x is just an equation of a straight line. If we consider the gradient being 18 and if it has no y-intercept, in other words, it starts from the center moving upwards. I mean from 0. It starts from 0, or which is the origin, moving upwards. So when we reach here, we also go to now between B. Remember, this was A, you have A, you have B. Now I go to again maybe between B and C. Between B and C, what is the equation? Look at segment B. The equation for bending moment is 4x plus 28. So 4x plus 28, when the distance x is equal to 2. Remember, this is 2. Then you have this one being 5. Then you have it. Just as long as you keep this 4, you add 3, you get 5. You add 2, you get 7. That's what I'm meaning. At x is equal to 2, I have 2 times 4. Remember, we have said the equation, the governing equation, 4x plus 28. I get 2 times 4, you get 8 plus 28. It still gives you, it is starting, 36. It gives you 28 plus 8 gives you 36, which means our equation, our bending moment is starting from here, 36. Then we follow the equation of a line, which is 4x. Now you have 4x plus 28. So now let me go to, since I know this is the equation of a straight line, I just go to at x equal to 5. At x is equal to 5, this is going to be 20. 4 times 5, it becomes 20, plus 28 becomes 48. It means it is linearly increasing up to 20. It is up to 48. Between C and D, what is the governing equation? The governing equation is negative 24x plus 168. So we have negative 24x plus. Now, let me put also, I'm still at 5. I want to know what is, if I use this equation, what is the value of the bending moment at x is equal to 5. So I have negative 24 times 5 plus 168. It gives me 48. It means still it will start from here. Now, what is the bending moment at 7 or at x equal to 7? It means I have negative 24 times 7 plus 168. The answer is 0, meaning it is now having a negative gradient. In other words, when you just look at it, arrange it in the form of y is equal to mx plus c. It means the intercept is 168, the y-intercept is 168, and it has a gradient of negative 24. Yes, meaning it will be a falling line. So it means I will draw it from 48 coming to 0. So the bending moment becomes 0. So this is a shear force diagram, and this is a bending moment diagram. Maybe to examine ourselves, let me share my screen again on somewhere we need to be certain of what we have been calculating. Maybe we can just look at the final answer. Okay. Yeah, green. If you check properly, you see that we have it correct and very well correct, or very much correct. So you can look at it, you see here our reactions are 18, here at D it is 24, and when you relate with what we just drew, we said it also starts, the shear force starts from 0 to 18, is still 18, then it reduces by 14 to go to 4, then it becomes a constant between C and D. Then at 20, at C, there is a force that is pointing vertically downwards. Then you move through a 4, okay, through a 4. Okay, maybe you just get 28 minus 4. It will give you what value is going to be here. This value is going to be negative 24, because you are saying down here below, beyond a 0 mark, the values are going to be negative. So if I'm falling by 28, it means if I already have a 4, I need to fall by 24. So what value is going to be here? Automatically it is going to be negative 24. Then I move and I remit a 24, I come back to 0. If I move through a 24 positive force, then I come back to 0 and I complete my shear force diagram. I go back to drawing a bending moment diagram. You see, at the x is equal to 0, the bending moment is 0 because we said we have 18x. At this next point, at x is equal to 2, we have 18 times 2, which becomes 36. Then we have another governing equation between b and c, which we said is let me check it. Maybe I can. It is 4x plus 28. And when we put at x is equal to 2, we have 4 times 2, which becomes 8 plus 28. It gives you 36. Then I again move at x is equal to 5. If I get 4 times 5, I get 20 plus 28, I get 48. Then again I use the other equation, which is for segment C and D, and that will be negative 24x plus 168. If I get negative 24 times maybe 5, I'll get negative 120, I add there 168, I'll get 48. Then I move to x is equal to 7. At x is equal to 7, I get negative 24 times 7, I get negative 168. Remember, I have to add there 168. It cancels out to become 0. That means I'll draw my line from 48 falling to 0 again. And that will mark the end of that particular problem. Members, if there is no question, I beg submit.